Carnot actually tried to look at efficiency of various kinds of engines. He had a suspicion that you can't increase efficiency to become one. You can't use all the heat supplied. He understood some amount of energy conservation part, so he knew that actually whatever energy you are getting in as heat, you are unable to use it, you need to throw it out. You need to throw out a part of it. And he realized that there was some issue with this, so he tried to formalize this whole thing. In fact, he developed a large part of the Carnot cycle, thermodynamics, the basic idea behind it, after which people realized that there is something deep here. He did it for engines, but actually there is something which is very significant about the whole universe. Okay, so the point with thermodynamics is while it studies engines and some gas and going back and forth, it is going to make statements about the entire universe. It will talk about what stars can do, it will talk about what the universe can do. In fact, in some sense it talks about the arrow of time. It talks about why time moves in one particular direction. Now we never get down to actually studying any of these, but thermodynamics at its basic level is a very fundamental science. Okay, anyway, let us come back to this idea. So what Carnot did was to argue that if I set up a system which was perfect, absolutely clean and clear, there was no losses anywhere at no point, it was completely reversible engine, this would be the most efficient engine, because if it was irreversible, we will basically increase losses overall. So his point was, but even with the reversible engine, you cannot get the best efficiency possible. Okay. He knew one interesting idea, which all of us know, but he converted this interesting idea into something else. And the idea is that if I had an object which was at a higher temperature and you had an object at a lower temperature, on its own heat flows from the higher temperature to the lower temperature. You can't make heat go from the lower temperature to the higher temperature. Okay. So his point was, I can see that heat is going to go this way, but if I do it in a way where it is reversible, I should do this in such a way that this low temperature and high temperature, the difference should be very minimal. Because if I had a large heat flow like that from high to low, then it won't flow back, it is not reversible. So he said that basically if I want to transfer this heat in a reversible way, it won't go back on this, in this direction. So transfer it such that these two are the same temperature. So any heat transfer that happens, if you want it to be reversible, must happen such that both the bodies are almost at the same temperature, or at the same temperature you transfer very small amount slowly, so that it can be reversed. So he wants to basically look at reversible engines, because the assumption here is if you have a reversible engine, that will be the best efficiency engine. It's okay even if it is low. He wanted to get a theoretical limit for what is possible. Now Carnot's assumption was that you are going to have only two temperatures, and all that we are doing with Carnot cycle is to talk about two temperatures. You can have many reversible engines which actually have many different temperatures. When you talk about Carnot cycle, you are talking about two temperatures. So I only have two temperatures, T1 and T2. You don't have anything else. You are not allowed T1, T2, T3, T4, T5. Not allowed. Only two temperatures. Okay. Now if you make both equal, then of course there is no big difference that you can do. So we will start with something at temperature T1. Some pressure, some volume, some temperature T1. Now if I want to supply heat to this fellow, I have only two temperatures, right? I want to supply heat to this fellow in a reversible way. What should be the temperature of my source? T1. Because if my temperature of the source was less than T1, it won't supply. If the temperature of my source was more than T1, it will supply, but it will supply in an irreversible way because you can't supply it back to that fellow. So you must have a source which is actually supplying heat at T1, and if that is also at T1, this is also at T1, as I am supplying heat, the temperature remains T1. So if I have a gas and I am supplying heat to this gas from this source at temperature T1, this is also at T1, heat is being supplied. As it slowly expands, it's always at thermal equilibrium between this and that. So what is this guy's temperature? T1, 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 T1. What kind of process is that? Isothermal process. It will expand isothermally, which means it will do this. And what will be the temperature at that point? T1. Now, you've got some work out of this process. But the thing is, if at this stage, I want to maximize some more work. If I try to take it back, well, my work done will be 0. So what I want to do is I have a sink which is at temperature T2, which will take heat. This gave heat, right? Now I want to take heat. But if I took heat back at T1, which I can do, I can also take back heat at T1, no problem, by compressing it back. But if I compressed it at this point, what is going to happen? 0 work. So before I do that, I must reduce pressure. If you remember last time when we discussed itself, we said that if you did work at this point and you want positive work, you better go down and then go back. So that the work that you are spending to compress, you have got some work when you are expanding. But the work that you have to spend to compress it back should not be equal to the work that you received, no? Then of course your efficiency is low. I would like it to be as low as possible. So one possibility is to drop it down like this. But there is an issue. Because if I drop it vertically down, how much was the work done? 0. Yes, my temperature has come down, my work done was 0, but I did supply heat. Think about it. I did supply heat if I come down like this, right? But heat at what temperature? Changing temperature from T1 to T2. I supplied heat, which then meant it has become irreversible. Because somebody else has to receive it. If there were many different sinks at different temperatures receiving it, we can receive it back from them. But the only sink that is available is T2. I told you there are only 2 temperatures available. So if this guy is supplying heat, it cannot supply it to that source, that big heats. Well, sink and source are just 2 terms, right? One of them is at temperature T1, which is higher than temperature T2. If I am going to be lower than temperature T1, I can't supply heat to this guy. The only other option is to supply it to T2, because there are only 2 things allowed. What if I had an in between T1.5, T1.6, 1.7? Yes, you could have supplied to all of them. But the whole assumption is I have only one source and one sink. That means I have only T1 and T2. And by the way, this is limited to T1 and T2. What will happen if I have T1, T2, T3? You will have to rework this entire plan. But given that you have only T1 and T2, what Carnot's argument was, well, if I go like this, I am now supplying from T1 into a sink which is at T2, then I am going down to a temperature of T1 by some slight minus delta, and I am supplying it to T2. Now there is a big temperature difference, and the heat that you supply like this cannot be reversed, because you are supplying it into a sink which is at a lower temperature, and therefore you are in some sense losing out, okay, the quality of energy, which I will come back to in a minute. We will talk a little bit about that. Carnot didn't know about the idea of entropy, but this is the idea of entropy. He realized that reversibility and entropy have some very significant connection. Anyway, so that means I must go from T1 to T2 in a way where I am not giving out heat until I get to T2. Is there a nice way in which you can go from T1 to T2 without giving heat? Adiabatic process, absolutely. So you go from here to there in an adiabatic process. So his argument was this has to be isothermal, because here I am taking in heat at constant temperature. This has to be adiabatic, because I should not give out heat at anything which is not T2. But once I get to T2, now I would like to give out the heat. By doing what? Isothermally handing over the heat to this fellow. So I remove this guy I put another sink here, another whatever heat bath at temperature T2, but the gas has also come down to T2. It is now somewhere there. Okay, it expanded from here to here isothermally and from here to there adiabatically. All this was work done, which is good. Work. Okay, then now I am going to compress it and I am going to continue to compress it further. I am going to basically go all the way there. But I want to first compress it isothermally. So I put this T2, now the heat goes this way. Okay, so I compress it isothermally like that. But this is isothermally at temperature T2. Okay, and then from here to there I compress it adiabatically. But that time the temperature changes from T2 to T1, but I am not giving any heat, so I am not really changing anything outside. So it goes from T2 to T1, but this is adiabatic. He said at no process, no step of this process did I do something which was irreversible. Because if I had given it from a high temperature to a low temperature, I would have done something irreversible, but I did not do it. Because I took heat in an isothermal way. Here I did change temperature, but that time I never threw out any heat. Then here again I did something isothermally where I gave out heat, but it was isothermal. Okay, so I never gave heat from one level to another level where it was not reversible. And then this was adiabatic, so I can always reverse it. This is the best possibility. What is the efficiency of this possibility? That is the question. Okay. Well, the work done by the heat supplied. But what heat supplied? Only this heat supplied. Because there was no heat supplied for that part. And what about this one? No need to worry. Why? Because there was the heat thrown out. That is not part of efficiency. No heat supplied. But for work done, I need to worry about this entire area. Do I know this area? What is the area? We can calculate that area, right? How much is that area? Huh? P1 B1 V2 by V1. Right? We can find out that area and then we can find out this area. Then we can find out this area and we can find that area and subtract. Or we can just look at something and think a little bit and say, how much heat did I supply from here to there? What was the heat supply? Let us say it was Q1. What was the heat supplied here? 0. Okay. So this was Q1, that was 0. And what about this? Q2 heat was rejected out and that was 0. So what will be the work? Q1 minus Q2. So my efficiency, which should be W by Q1, is actually Q1 minus Q2 by Q1. Correct? Which must be 1 minus Q2 by Q1. I mean, this is just first law of thermodynamics. I am not actually calculated work. I am cheating. But if you think a little about it, can we find out what is Q1? How will we find out what is Q1? We can't use NCV delta T or NC delta T, can we? Why not? Because it's isothermal process. Okay. Now, it turns out that this will be T2 by T1. Why will it be T2 by T1? Huh? How do you know? Let us think about that idea first. Okay, is the internal energy the same? Right? So at this point, this fellow has some internal energy. At that point, this fellow has some internal energy. Right? So what is the internal energy function of? Temperature. So the internal energy will be some constant times temperature. This internal energy will be constant times this temperature. Now the key point about this business, right? Let us try and understand this very quickly. Heat is energy. But why do we separate heat and work? Why is the first law of thermodynamics saying heat is delta U plus W? Why are we separating heat and work? If this is also energy, that's also energy. Because you can't go from heat to work fully, but you can go from work to heat fully. Potential energy can fully become kinetic energy. Kinetic energy can become heat energy, but heat energy cannot become kinetic energy fully. Heat energy cannot become potential energy fully. Now, the basic point is, if you think of it this way, heat is one of the worst forms of energy. But there are many types of heat energies. All other forms of energy are the same, but heat itself has many levels of dirtiness, if you want to think of it that way. Okay. So the way I look at it is to say, this ball represents energy. This ball represents energy. So if I have, like, let us say 100 different balls like this, I have 100 units of energy. Okay. Now if I give you 5 units of energy, I have 95. So the total amount of energy that I have, if I pass it on, it keeps reducing. So the total energy that is there in the universe is conserved. But I can make this ball dirty by spitting on it. So that means this energy is now dirty energy. But I can make it dirtier and even more dirty, right, than what it was. I can have 1 unit of spit on it, I can use 2 units of spit on it, I can have 10 units of spit on it. A ball with 10 units of spit, if I pass it on to you, will you touch it? Probably no, right? But so if you think about this, now the fact that you have dirtier energy tells you something about temperature. Reasonably clean heat energy is high temperature. Okay, now really dirty heat energy is low temperature. Now what does this mean? If I had one system, this has heat, that also has heat in it. They have different temperatures. Now what happens? Imagine this case. Now imagine this fellow generally has 1000 balls here with 1 unit of spit, or let's say 10 units of spit. So it has 1000 units of energy with 10 units of spit. Okay. Now we look at its cleanliness here, indicator is 1000 by 10, we'll call it 100. So I will say that this guy has 100 as the ratio. Okay. More energy compared to the spit, more clean. So this is the cleanliness ratio. Okay. And I am going to call it temperature. So this fellow's temperature is 100. Now imagine that this guy has, let us say, 1000 units also of heat, but has 1000 units of spit. Okay, so per unit it is 1. So this guy's temperature I am going to claim is 1. Obviously it's more dirty, no? This is cleaner, this is dirtier. Agreed? Now the basic point you have to understand is, if I took these two balls and they had 1 unit of spit, or let's say they both had 1 unit of spit each, how many units of spit do I have? 2. It is possible that I can do this to this ball and transfer the spit here. Now this ball has become clean and I throw this at you, you catch it. What I have given you is pure energy, we will call it work. But what about this guy? The 2 units of spit is sitting here. Now imagine I took this one also and cleaned it up. But I have to clean it up onto something, right? And that something now becomes very dirty. You can take 1000 units of heat and clean up this 10 units of spit. But if I did that with 999 balls, I pulled it out. That means what is going to happen is, if I took out 999 of these balls and made them perfect pure energy with no spit, that one ball will end up with 10 units of spit. So you have one ball with 10 units of spit. Now if you try to pass it on to this guy will say, no, I am dirty, but I am not as dirty as this. How dirty am I? One spit per ball. You are trying to give me 10 spit units for one ball. No. You give me 10 balls and give me 10 units of spit, I'll take it. So that means, if I want to hand over to this guy, I must give 10 units of spit. If I want to give 10 units of spit, I must give 10 units of energy. Otherwise, this guy won't accept. Why? This guy is cleaner than the ball I am giving. Okay, now you said you will not take a ball with spit, but suppose you already had lots of balls which had a lot of spit in it. If what I gave was cleaner than what you already have, there is no reason why you won't accept. If what I was giving was dirtier than what you had, you won't accept. So if I am now giving equal to this guy's dirtiness, will you accept? No problem. But then what is the amount of energy that I can completely clean up? 990. Okay, do you now understand why heat will go from high temperature to low temperature? If it directly goes from high temperature to low temperature, just imagine. High temperature is saying my dirtiness level is very less. Will the low temperature accept that heat? No problem, take it. In fact, that guy is very happy to accept. But will it go this way? Because this is really dirty energy. So you are not going to accept. Now, what Carnot and lots of other people and who are basically running engines, what do? We say, here I have temperature 1, here I have temperature 2, I am sending out energy Q, which has some amount of spit in it. How much spit? Q by spit is temperature. So Q by temperature is the amount of spit. So this comes with how much spit? Q by T1 plus Q. Q is the, these are two different things. This is the amount of spit, this is the amount of energy. Now the point is, the spit has to be transferred. You can't just say, I'll give you 0 and take all the spit alone, right? I want to take an engine which will produce work. Now work is spitless energy. Okay. Now if I want energy that's coming out which is pure, I have cleaned it up from this, from the Q. But I have to parcel some little bit and send it there, right? If I gave this fellow Q, this guy is willing to accept. Why? Because this fellow's temperature is T2 lower than T1. It's able to accept. But you don't need to give that much energy to this fellow. Okay, if I pulled Q1 out, the amount of spit was Q1 by T1. I must transfer the full spit there. But you see, this guy's temperature is T2. I can transfer Q2 by T2. If I transfer lesser amount of energy, also this guy is happy. Look at this fellow. I could have transferred 1000 units of energy with 10 units of spit. This guy would have accepted. But why waste it? Efficiently, what you do is you only give this guy 10 because this guy only wants 10. So you use the fact this guy is willing to take 10 units of energy for 10 units of spit to clean up 990 units of energy. So think of it like that. So what I need to transfer to this guy is Q2 by T2, which has to be equal to Q1 by T1. The amount of spit transferred is the same, which means I clean up Q1 minus Q2 units of energy. So what is the rule then? Q1 by T1 is equal to Q2 by T2. Okay, so Q2 by Q1 is T2 by T1. So this basically becomes 1 minus T2 by T1. Now this is called entropy. The symbol for entropy is S. Entropy is like spit. And the general rule for the universe is you can add spit, you can increase the amount of spit, but you can't decrease the amount of spit. Okay, but spit makes energy dirty, and all heat energy also has some entropy in it. Okay, now this formula is not directly correct, so usually we write this by saying dq by T is ds. I have written it as q by T is s. That's the only difference. Okay, but please spend some time, think about this idea, because that's exactly what you are doing when you are doing Carnot cycle. Okay.